Let's now talk about galvanic cell problems. So we're going to study in great detail over the course of this video galvanic cells and how you can solve different types of questions that you can see that involve galvanic cells. We have this example problem that we're going to work through here that's going to have 4 parts to it. We're told that we have a galvanic cell that's constructed using a copper electrode immersed in a 1 molar copper 2 plus solution, and we have an aluminum electrode that's immersed in a 1 molar Al3 plus solution. Now, this term galvanic cell is really important because when you see the term galvanic cell, that tells you that the cell potential that you have must be positive. And that's going to be beneficial for us to keep in our minds as we solve the 4 parts to this problem. We're going to determine what the standard cell potential is. We're going to calculate the standard value of delta G for the redox reaction that occurs in this cell. We're going to determine which way the electrons flow. And we'll also talk about the salt bridge and which way the ions in the salt bridge flow. The first thing that we can do is take a look at a sort of crude drawing of the cell just to get a visual of what's going on. I find it really helpful to have visuals of things. So this is a sketch of our cell. We have a beaker in which we place a Cu2 plus solution and a solid piece of copper. We have a second beaker that contains our Al3 plus solution and a solid piece of aluminum. You have to have a wire that connects the two, and you also have to have a salt bridge, and you can use any strong electrolyte or any ionic, soluble ionic compound for that. So I chose to use KNO3 so that we have K plus and NO3 minus ions. So this is our crude sketch of the cell to kind of visualize what this is going to look like. Now let's talk about how we can write reactions and how we can figure out what it is that's being oxidized and what it is that's being reduced in the redox reaction that occurs here. To do that, you're going to have to look at this thing called the table of standard reduction potentials. This table contains a series of reduction half reactions, and next to each of them is listed what the reduction potential is, or that is what the half cell potential would be. So, for instance, if you were to do the reduction of F2 to F minus, that has a reduction potential of 2.87 volts. Or if you were to reduce H plus to H2 gas, that has a reduction potential of 0 volts. You can kind of think of these standard reduction potentials as being analogous to maybe altitudes or elevations from sea level, right? If you were talking about being on a hill that was 3,000 feet high, that would indicate that you were 3,000 feet above sea level. That's what we define as our zero when we're talking about elevation. Now, in electrochemistry, we define our sea level as being the standard reduction potential for H plus ions. That's the sea level that we have. And then the standard reduction potentials of all the other things that are listed on this table are measured relative to that anchor point. Right. Now, having looked at the table of standard reduction potentials, let's figure out how you're going to determine what's being oxidized and what's being reduced. It's important to keep in mind that you must have one oxidation half reaction and one reduction half reaction. The electrons have to be on opposite sides of the two equations, right? And in the table of standard reduction potentials, they're all reduction half reactions, and electrons are on the left-hand side of every single one of those equations, right? So we need to figure out which of the two half reactions has to be converted into an oxidation half reaction. We have this guiding principle that I've mentioned before, that in a galvanic cell, you must have a positive standard cell potential. And so with that in mind, let's think about which of the two half reactions should be converted into an oxidation half reaction. Should it be the one for the Cu2 plus, or should it be the one for the Al3 plus? And I've included what their standard reduction potentials are so that you can figure out the answer to this problem. Take a moment to put in your answer. All right, having given you a moment to think it over, let's talk about the answer here. So if we want to have a positive full cell potential, then we should consider reversing the half reaction that involves Al3+, because if you were to reverse that half reaction, you'll now have electrons on the right-hand side of the equation. This will now mean Al is losing electrons, right? So you will have a oxidation half reaction here, and you'll flip the sign of E naught from negative 1.66 volts to positive 1.66 volts, and that will give you a positive full cell potential at standard conditions. So we need to reverse the half reaction for the Al3+, and in doing so, we'll convert this reduction half reaction into an oxidation half reaction. The answer here is B. Now, the guiding principle that we have when we're dealing with galvanic cell problems is we find the two half reactions that correspond to the things that we have in our galvanic cell, right? In this case, it's the copper and copper 2+ and the Al and Al3+. You find these two half reactions and you look at the E naught values, and the reaction that has the greater value of E naught will remain the same, and the reaction that has the lower value of E naught needs to be reversed. And if you reverse the half reaction that has the lower value of E naught, you will guarantee that you will always end up with a positive full cell potential, which is the requirement of a galvanic cell. So that's the idea that you use, and you can generalize that to thinking about any other galvanic cell problem. Now, in addition to writing out the half reactions, we can identify what the anode and the cathode are in this cell. So the anode is the place where the oxidation half reaction occurs. And we've now determined that after reversing the aluminum reaction, this is now an oxidation half reaction. Al is losing electrons, getting oxidized to Al3+. So the Al3+ compartment is the anode. Reduction occurs at the cathode, and we kept the Cu2+ half reaction the same. Cu2+ is gaining electrons, it's being reduced to Cu solid. And so we would say that the copper 2+ copper compartment is the cathode. Now, there's a mnemonic that you can use to remember what the anode and the cathode are, and the mnemonic is anox red cat. So I kind of underlined those letters in here, right? So anox, anode is the oxidation half cell, and red cat, reduction occurs at the cathode, so that you can remember which one is which. Now, in an electrochemical cell, electrons will always flow from the anode to the cathode. And the reason why that happens is because at the anode, you are producing electrons, right? And so this is where you make the electrons, and then those electrons have to flow through the wire to the cathode where they're needed to cause this reduction half reaction to occur, right? So the electrons go from where they're being made to where they're needed. And as a result, electrons will always flow from the anode to the cathode. With all of that in mind, we can incorporate this information into the drawing of the electrochemical cell that we saw a few minutes ago. We've now determined that in the half cell containing copper and copper 2+, the half reaction is Cu2 plus 2 electrons goes to Cu solid. And we've determined that in the half cell that contains the aluminum and the Al3+, aluminum is being oxidized, going from Al to Al3+ plus 3 electrons. Furthermore, we've identified what the anode and the cathode are here, right? So the anode is where oxidation occurs, anox. Aluminum is oxidized. So we can say that this is the anode, and Cu2+ is reduced. And so that's the cathode, red cat. And additionally, we talked about the direction of electron flow and said that electrons will always flow from the anode to the cathode, because at the anode, you are producing electrons, right? So we make electrons here, and we'll say make electrons here. And you need the electrons over at the cathode. And so you're going to take the electrons and send them from where they're made to where they're needed. The direction of electron flow will be from the anode to the cathode, just like that. All right, so we've already answered one part of the question that the problem asked us to deal with here, right? We've found what the direction of electron flow is. Let's now talk about how we can find the standard cell potential and the delta G standard for the reaction that occurs. To find the standard cell potential, you're going to balance the electrons so that you have a common coefficient of E-. But when you do that, you cannot change the E naught values for each of the two half reactions. The E naught values are intrinsic properties of the system that you're studying, and they do not scale with the size of the object that you're dealing with. We could think of some other properties that are also intrinsic properties of a system that don't scale with the size of the system. Color would be one of them. You can imagine maybe if you have a cup that is blue, it doesn't matter if the cup is small, like a little, teacup, or if it's a giant mug, right? It's all blue. It doesn't matter how big or how small it is. That's not something that scales with the size of your system. It's an intrinsic property of the material that you're looking at. And the same thing applies for the E naught values that we deal with here. All right, after balancing the electrons, you can add up the two half reactions to get the overall reaction, and then you'll add up the E naught values to get what the standard cell potential is. So we have our two half reactions that we've written here, the one for the oxidation of the aluminum and the one for the reduction of the copper 2+, and we'll balance the electrons, getting a common coefficient of E-. We're going to recognize we have a 3 in front of one of them and a 2 in front of the other, and so the lowest common multiple that we have here is going to be 6. We have to make a common coefficient of 6 here. We're going to multiply the aluminum half reaction by 2, and multiply the copper half reaction by 3, giving us the common coefficient of 6. Remember that you do not change the E naught values because those are intrinsic properties of these materials, so those have to stay the same. Then, what you can do is add up the two half reactions to get the overall. What we have here is 2Al solid plus 3Cu2 going to 2Al3 plus 3Cu solid. And the 6 electrons cancel out here, right? Because you have 6 electrons on the right-hand side of the aluminum half reaction and 6 electrons on the left-hand side of the copper half reaction. The standard cell potential is going to be the 1.66 from the aluminum plus the 0.34 from the copper 2+ half reaction. So that comes up to 2 volts. That would be the voltage that's supplied by this crude battery that you can generate. Next, we could talk about how you can find what the delta G standard is for the overall reaction that we've just written here. Standard cell potential is related to the change in Gibbs free energy according to the following equation. Delta G standard is equal to negative NF E naught for the cell. And so in this equation, N refers to the number of moles of electrons that get transferred. F is a constant called Faraday's constant, and this tells you the amount of charge that gets transferred per every mole of electrons that get transferred. Faraday's constant is a constant. It has a given value of 96,485 coulombs per mole of electrons. What this value is telling you is that 1 mole of electrons carries a total charge of 96,485 coulombs. All right, so with that in mind, we can go about calculating the standard change in Gibbs free energy for this reaction. We'll put back up the two half reactions that we've written out and the overall reaction with the standard cell potential, and then we'll use our delta G equation. So delta G standard is equal to negative N. N refers to the number of moles of electrons that have been transferred here, and that will again correspond to the coefficient of E-. The coefficient of E- here is going to be 6, and so N is equal to 6. 6 moles of electrons are being transferred. So 6 moles of electrons times Faraday's constant, 96,485 coulombs per mole of electrons, times the standard cell potential, which is 2 volts. And I'll mention something in terms of the units. I'll remind you that 1 volt is the same thing as 1 joule per coulomb. And so I can re-express this. Instead of saying 2 volts, I can say that it's 2 joules per coulomb. And doing this will help you to see how the units cancel out. The moles of electrons cancel out, the coulombs cancel out, and I'm left with just units of joules. Now, if you were to put this into your calculator right now, you'd end up getting a number that is outrageously large. And so what I'm going to do is make the number a little bit more manageable by converting it to kilojoules. So 1 kilojoule is 1,000 joules, and we'll cancel out that to get to kilojoules. And what you'll find is that the standard value of delta G for this reaction is negative 1,158 kilojoules. And so that would represent, right, the energy that gets released as you do this chemical reaction, and allows you to convert between the cell potential to energy. All right, so let's take another look back at the sketch of the cell that we've been describing here throughout this problem. We have previously identified that the copper 2 plus half cell is our cathode because that's where the reduction took place, and that the aluminum Al3 plus half cell was the anode because that was where oxidation took place. We talked about how electrons always flow from the anode to the cathode, so they're like flowing from the Al3 plus to the Cu2 plus. We calculated what the half cell potential was at standard conditions, and we calculated what the standard value of delta G was. There was one last piece of information that we were asked to determine, and that is the direction that the salt bridge ions flow. And let's talk about how we get that answer. The idea is to look carefully at what is going on in these two half reactions and to think about how the salt bridge can help you to balance charge. When you take a look at the anode, you are making Al3 plus here, right? You're making positive charge. And you can't just have an excess of positive charge in the solution. If you had a buildup of positive charge in the solution, there would come to a point where there would be no motivation for the electrons to leave, and the reaction would come to a halt. And so we have to balance this buildup of positive charge with some negative charge. We have to introduce some negative charge to balance things. So we have to add minus charge to balance, and that negative charge comes from the salt bridge. You can think about what ion in the salt bridge has negative charge, and that is going to be the nitrate ion. And so NO3 minus ions from the salt bridge will flow into here. So that these NO3 minus ions will just flow right in to balance the charge. And then we could think about what's going on at the cathode. So at the cathode, we are taking Cu2 plus, adding electrons to it to make Cu solid. So at the cathode, you are removing positive charge from the solution. And so you have to replenish that. And to replenish it, you'll use the K plus ions from the salt bridge. So the K plus ions from the salt bridge will flow into the cathode compartment. That helps you to balance charge in this cell and allows the reaction to continue and prevents charge buildup. Now, this is the way that it's always going to end up working in one of these cells. You're going to have a flow of the cation from the salt bridge into the cathode because the cation has positive charge, and that replaces the positive charge that's being eliminated from the solution. And you'll always have the anion from the salt bridge flow into the anode compartment because that negative charge balances out the positive charge that gets produced at the anode. So in the salt bridge, cations always flow to the cathode, anions always flow to the anode. And it's a little easier to remember when you see it this way, right? Because these terms both start with the same letters, right? So cations to the cathode, anions to the anode. And actually, this is where we get the words cation and anion from. Now let's talk about why the standard cell potentials do not depend on the number of moles, or they don't scale with the size of the system, or why they are an intrinsic property of the reaction that you're describing. We'll first start by considering the reaction that we've just been discussing over the course of this entire problem here, right? 2Al solid plus 3Cu2 plus goes to 3Cu solid plus 2Al3 plus. And we found that the standard value of delta G for this reaction was negative 1158 kilojoules. We also found that the standard full cell potential was 2 volts. Let's think about what would happen if we multiply this reaction by 2. So now that's going to give us 4Al solid plus 6Cu2 plus going to 6Cu solid plus 4Al3 plus. We've learned previously that some thermodynamic variables, such as delta H and delta G, do scale with the size of the system. So if you multiply a reaction by 2, you would multiply the delta H by 2, and you multiply the delta G by 2 as well. So the value of delta G will be 2 times negative 1158 kilojoules. However, the value of E naught for the cell will still be 2 volts. And let's see why that's the case here. Delta G and E naught for the cell can be related according to the equation delta G standard equals negative NF E naught for the cell. And so we don't just think about the value of delta G naught and the value of E naught, we also have to think about N, the number of moles of electrons that are transferred. Now, we've talked about how you get that number from looking at the coefficient in front of E minus in the balanced equations. And when we looked at the original form of the equation with 2Al solid and 3Cu2 plus, we found the coefficient of E minus was 6, so N was equal to 6. 6 moles of electrons were transferred. If you multiply the reaction by 2, then all of the coefficients are being multiplied by 2, including the coefficient of E minus. And so now you're going to have 12 moles of electrons being transferred. N will be equal to 12. And with that in mind, let's now convert the value of delta G standard back into the value of E standard for the cell to see that it still remains 2 volts. So we'll begin by dividing both sides of the equation by negative NF. So that gives us negative delta G standard over NF. And then we can plug in the numbers. So E naught for the cell will be equal to negative. The delta G was 2 times negative 1158 kilojoules. Over 12 moles of electrons. And Faraday's constant, 96,485 coulombs per mole of electrons. Now, if you plug all of this into your calculator right now, you'll get a number that's going to be a little bit weird because the units that you have right now are a little bit weird. So let's talk about the units. The moles of electrons cancel out, and what you're left with is kilojoules per coulomb. However, if we wanted to express potential units of volts, that is joules per coulomb. So I'm going to convert the kilojoules into joules. 1,000 joules is 1 kilojoule. And now what I'm going to be left with is the kilojoules canceling out, and I get joules per coulomb. And that is a nice way to write the units because when we write joules per coulomb, that's the same thing as a volt. And the number that you get when you plug this into your calculator comes out to 2.00. And so you'll find this standard cell potential still remains 2 volts. So the reason why it is that the standard cell potential is not scaling with the size of the system is because, yes, you do double the value of delta G, so you make the numerator bigger by a factor of 2, but you're also doubling the number of moles of electrons, and so that makes the denominator bigger by a factor of 2, and that all serves to keep the value of E naught for the cell constant, regardless of what you multiply the reaction by. Lastly, we could think about what would happen if you were to reverse the reaction, and we'll talk about why that would be an important thing for us to do in just a moment. So 2Al3 plus 3Cu solid going to 3Cu2 plus and 2Al solid. So if you reverse the reaction, that's going to change the sign of delta G standard. So the delta G standard will now be positive 1158 kilojoules. And also, when you reverse the reaction, that's going to change the sign of the standard cell potential, right? You could go through the equation delta G standard equals negative NF E naught for the cell to show that to yourself. But when you reverse it, it will change the sign. So the standard cell potential will now be negative 2.00 volts. Let's think about what that means. Is this reaction still spontaneous? No. And we know that because delta G standard is greater than 0, and because the cell potential is negative. Now, why do we care that this reaction is not spontaneous? Why would we care about writing the reaction in reverse? I'll remind you that these galvanic cells that we've been describing are like a crude version of a battery. And you can imagine that when you get a battery and it initially supplies that 2 volt, and you could use it to do whatever you want to do with the battery, right? It powers a light bulb, it powers a laptop, it powers your cell phone or something like that. But over time, as you do the reaction, you will find that the voltage will steadily decline until the battery goes dead. And when the battery goes dead, you want to be able to recharge it. To recharge the battery, you would have to reverse the reaction, taking the products that you made and converting them back into the reactants so that you could do the reaction again and reuse the battery, right? So that's why we're interested in reversing the reaction. That's like similar to recharging a battery. This is, however, not a spontaneous process. We just determined that. The delta G standard is positive for it. So let's think about how we could make the process spontaneous. I'll remind you that for a non-spontaneous process, it requires a continuous external intervention to make that happen. So what would be the continuous external intervention that you could place on this system to force the reaction to occur? Think about what you have to do when you want to recharge your batteries. You have to go ahead and plug them into the wall and supply some external electrical current in order to drive the reaction in the reverse direction. That is the continuous external intervention that you would need to place on the system in order to force this non-spontaneous reaction to occur, in order to go back to the reactants so that you can then reuse the battery. Now, the use of this external current to force the non-spontaneous reaction to occur is something called electrolysis, which is what we will discuss in the next video.